Welcome to my channel. Today we look at revision questions and their answers. These are part of questions that I've given in a continuous assessment test in November 2022. So I just want to show you how to go through these questions and get the answers. The first question is here. We're supposed to tell whether this system here has a unique solution or whether it has infinitely many solutions. Part C, whether it has infinitely many solutions, and part D, whether it has no solution. Part B is whether it has finitely many solutions. There is a video you can check if you've not seen it. I've given a video where I was showing the nature of solutions of a system. In that video, I covered these concepts in details. And I'm aware that for those who watch that video can tell, if given a system, they can tell whether the system has a unique solution or whether it has infinitely many solutions or whether it has no solution. So that is covered in one of my videos. But then we go through this question. Let's see how to do this question. So to do this question, you reduce the system to echelon form. And again, in another video, I had shown how to reduce a system to echelon form and also how to transform a system to reduced row echelon form. So you already have those concepts. So that means we should then move very fast because you already have the knowledge of what we are doing. Now, so let me write the system here. It is x minus y plus 3z is 4. And then we have x plus 0y plus z is 2. And we have x plus y minus z is 0. So reduce this to echelon form. Reduce to echelon form. Now, if you want, you can extract the augmented matrix and then reduce that augmented matrix to echelon form. But what I'll do is not that. What I'll be doing is I'll want to work with the equation, these equations to the end. I'll not be extracting the augmented matrix. So the first equation, remember, it is x minus y plus 3z is 4. And then the second equation, now I want a 0 at this point and a 0 at this point. So that means I'm using this coefficient of x, which is 1, to create a 0 here and a 0. That means I need to subtract the first equation from the second equation, and then subtract the first equation from the third equation to get a 0 at this point. So let me just do that. The first equation remains the way it is. Now, when I subtract it from the second equation, I would have a 0 here. Then the 0y minus y, which gives me y. And I have z minus 3z, which gives me minus 2z. What about here? 2 minus 4 gives me negative 2. Now let me now subtract the first equation from the third equation. X minus x will be 0. Y, take off this y, then minus y. That gives me 2y. Then I also have negative z here. Negative z minus 3z. That gives me negative 4z. And then I have 0 minus 4, which is negative 4. And of course, this third equation can be factorized, or not even factorize it. You can divide it through by 2, which is common. So let's just do that. So we'll divide this third equation. So the first equation, remember it is, and this is that plus is equals to 4. Just write it properly. This is 3z is equals to 4. The second equation, remember it is, that is y minus 2z is negative 2. This is negative 2. But now 2 is common here, so we have y. I'm dividing through by 2. That is 2z is negative 2. Now, I want to use this second equation to create a 0 here. So I'm subtracting the second equation from the third equation. I would have y minus x minus y plus 3z is 4. The second equation remains what it is. Now subtract the second equation from the third equation. I would have a 0 here. And then I would have a 0 here. So I have a 0 on the left side. And what do I have? I just have a 0 here. So I have a 0 on the left side and a 0 on the right side. So this is negative 2 minus negative 2 is equal to 0. Now, if we have 0 is equals to 0 in this last equation, so the last equation here tells us that this system has infinitely many solutions. Infinitely many solutions. Now, why do we say that it has infinitely many solutions? We say that because I can see that the free variable that we have here is only z. Only z is a free variable, so we can say that let z be 1. So when we say let z be 1, that means that we can get a different value, a value of y and a value of x. We can also say let z be 2. And if z is 2, then there'll be a different value of y, the different value of x. Z can also be 7. So we are not limited on the number of integers to choose for z. So z can take any integer. When z takes any integer, then y and x also takes on other different integers. So that means at the end of the day, this system can have as many solutions, very many solutions. And that's why we say it has infinitely many solutions. Not finitely many solutions, infinitely many solutions, because the integers are infinite. Now, so let's look at the next question. But this is how you are supposed to have done this question. You were just to reduce this to echelon form, and then you look at the last equation here and see if it is 0 is equals to 0. Means the system has infinite many solutions. In some cases, you will find that we have a non-zero value here. Non-zero value here. So if you have a non-zero value here, irrespective of what is here, irrespective of what is on the right side, if you have a non-zero value here, then it means that the system has a unique solution. The system has a unique solution. So if you have a non-zero value on the left side, and anything, whether 0 or non-zero on the right side, but I'm just focusing on the left side. So if the left side here has non-zero value, then the system would have a finite, not finite, would have a unique solution. would have a unique solution. That means it will have only one solution. Now, supposing this was non-zero, supposing the right side was non-zero, supposing the right side was non-zero, and the left side was 0, so that we have something like 0 is equal to 3. The right side is 0 and the left side is 0. Then it means the system has no solution. And a system that has no solution, we said, is called inconsistent. Inconsistent system. It has no solution. But one that has a solution is called consistent. Consistent system. So this system here that we are given here is consistent system, but it has infinitely many solutions. Now let's look at next question. About the next question. Now let's look at question 2. Question 2 says, the condition for these vectors to be linearly independent is that the constant, the scalar constant r, should not be equal to. So that means we need to find what h not be equal to so that these vectors become linearly independent. I just want to take you through what I showed in a different video on linear independence. By definition, when do we say that vectors u, v, and w are linearly independent? When do we say they are linearly independent? So that is very important for us so that we can solve this question. So we say that these vectors u, v, and w are linearly independent if you can obtain scalars ABC, all of them 0, all of them zeros, such that A times 2, B times B, C times W is 0. So if you can get scalars ABC, all of them zeros, such that A times U plus B times B plus C times W 0, then we say that the vectors, the 3 vectors are linearly independent. The other way is to determine the determinant. The other way is to determine the determinant of the matrix formed by these vectors. And if the determinant is not equal to 0, if the determinant is not equal to 0, then we say that the vectors are linearly independent. And we look at the 2 ways, those 2 ways. So let's begin the first way. And of course, you know what linear dependence. When do we say that vectors are linearly dependent? You already know that. And if you don't know, you can check the video that I showed earlier. Now, so we're now answering the question, let x, y, and z be the scalars. One condition that will make these scalars be zeros, all of them. So x times the first scalar, x times the first vector. You can write it in columns form or in row form, there's no problem. Y times the second vector. Z times the third vector. Will give us 0. So when you open these brackets, then you can have x plus 0y plus 3z is 0. And here we have 5x plus 6y plus 13z is 0. And here we have negative 2x plus ay, this is ay, minus 3z is 0. We reduce this to equal form just the same way we did for the first question. We did the first question with reduced to equal form. So we also do this, the same thing to this reduced to equal form. So the first equation remains what it is. So I'm reducing to equal form. Now, so multiply the first equation by 5 and subtract the result from the second equation. Multiply the first equation by 5, subtract the result from the second equation. We have 0 here. There was 6y. So I've written it in the place of y. So let me write it here, 6y. This by 5 will be 15. From this, you have negative 2. Negative 2z. So negative 2z. Now, multiply the first equation by 2 and add the result to the third equation. You would have ay. Multiply this by 2, you have 6. Add to this, 3z. And this is 0. Now, I can see that the second equation can be divided by 2. I just do that. Just do that. So the first equation is here. The second equation, I can divide by 2 to get 3y. And there is no problem, you can even leave it the way it is. Just divide this by 2. And the third equation remains as it is. Now, so what follows, therefore, is to use this second equation, equate as 0 here. So that I'll do by, or I can even divide, I should even have divided this equation by 3. I should even have divided by 3. And just do that. That would have even made our work easier. So let me just do that. So this second equation, instead of dividing by 2, let's just divide it by 3. So that we have a y, and this will be a third. That will have made our work even more easier. Now, so I want a 0 in this position. That means I multiply second equation by a and subtract the result from the third equation. So the first equation remains as it is. The second equation remains as it is. Now, I'm multiplying the second equation by a and subtracting the result from the third equation, because I want a 0 here and a 0 here. So a times a, now y times a, you get ay, subtract from ay, you have a 0. What about here? I would have negative a third az. That result I subtract from 3z. These are on like terms. In fact, I'll just end up with, if I were to simplify, this is what I would have. I would have something like that. 9z. 9z plus az. Of course, this can be factorized to be, let me just write it here. This space is not enough. Just try to squeeze it here. It is 9z plus lz out of 3 is equals to 4. Then write it in enough space. Enough squeeze it here. Just write it properly here. I want to write that last equation here so that you can see it, because it's that we shall use to get the condition that we are asked to show. I'm just rewriting this one. Just rewriting this. So I have x plus 3z is 0. The second one I had y minus a third z is 0. This last one was 9z plus lz out of 3 is 0. Now, so I want to use this last equation. And see. We already looked at the first question that we did. Question 1, we said that if the value is here, if the value here was to be 0, and this one also 0, then the system will have infinitely many solutions. But what we want is for the system to have a solution 0, 0, 0, a unique solution. And that unique solution should be 0, 0, 0. So that x should be 0, y should be 0, and z should be 0. Let me just look at the last equation and factorize it. The last equation that I have is 9 plus a z out of 3 is 0. So you can multiply by 3 on both sides, and when you do that, you have a plus 9. This is 9 plus a. Z is equal to 0. Now, if a is negative 9, we would have a 0 here. It's 9 plus a. So if a is negative 9, if a would be negative 9, we would have a 0 here. So we would have 0 is equal to 0. So if a is 0 is equal to 0 would then mean that the system would have infinitely many solutions. The system would have infinitely many solutions. Of course, this system has a solution. So if 0 is equal to 0, then it will have infinitely many solutions. So what we want is for it to have a unique solution. So for it to have a unique solution, I only need to say that a should not be equal to negative 9. A should not be equal to negative 9. So a should not be equal to negative 9. This is the condition. I looked at this. This was a plus, this was 9 plus a. 9 plus az is equal to 0. So I'm saying that if a is negative 9, then inside this bracket we'll be having a 0. So the left side will have a 0 and the right side will have a 0. And as we saw in the first question, if we have 0 is equal to 0 in the last equation here, it means that the system has infinite many solutions. And I said that for the system to have a unique solution, the value on the left side should be non-zero. The value on the left side should be non-zero. So for us to get a value that is non-zero, then a should not be equal to negative 9. So a should be any value but not negative 9. For example, if a is 2, then we will be having 11z is equal to 0. which would mean that Z would be 0. And so if Z is 0, you just put it here, and you will find that again Y will be 0. So if Y is 0 and Z is 0, put it here, put Z here, and X will also be 0. And that would mean that these vectors are linearly independent. So the condition that the question wanted us to find was this, that A should not be equal to -9. Now, I said that we can also use determinants. How are we to use a determinant? So we write these vectors as a matrix. This is 1, 5, -2, you have 0, now 6A, then you have 3, 13, and -3. Now we know that if for this vector to be linearly independent, the determinant should not be equal to 0. So this particular means determinant. So I want to use to get the determinant, and we know how to get the determinant. Very many ways of getting determinant. I showed videos on how to get determinant in so many ways. I want to get determinant along this first column because I can see the first column has a 0, and since it has a 0, it makes my work easier. I can even make this work easier by creating another 0 in this position. So how do I create a 0 here? I just take I want row 3, just take the current row 3 that we have, then subtract 3 row 1. And so what do I have? Row 1 remains as it is, row 1 remains that way, and then row 2 remains the way it is. And so I just want a 0 here. So row 1 times 3 subtract from row 3. So 1 times 3 subtract from that, I have a 0. And 5, this is 5. 5 times 3 would be 15. 15 from 13, I will have -2. And this would be multiplied by 3. So this by 3 would be -6. -6 subtracted from this would be 3. Now, so I'm getting determinant along the first column. So the determinant will be 1, this element here, times the determinant of the matrix that remains when I delete the row and the column of 1. The row and the column of this one. When deleted, I have 6 and -3, no, 2, 3. Remember that this determinant should not be equal to 0. So let's just get to the determinant first of all. This is determinant 18 minus, but this is also minus. So it's minus 2a. And so this is 18 plus 2. So this is the determinant. And so the condition for this vectors to be linearly independent, this determinant should be equal to 0. So 18 plus 2a should not be equal to 0. That means 2a should not be equal to -18. When I just cross -18 the other side of the equal sign. And that means a should not be equal to -9. So that is a question. That is how I would have done this question even using determinants. Is how I would have done it to find the condition that the question wanted. Now let's look at the other question. Now, in our earlier video, we also showed how to tell if sets are subspaces and how to tell if sets are vector spaces. But the question is about subspaces, and we say that a set A, let me call it even a subset. A subset would be okay. A subset a subset, let me use S of V, instead, I'm just giving you the definition to be a subspace. Instead to be a subspace if it meets the following conditions. If it meets the following conditions. Now, the first condition is that the element 0 or the vector 0 should be a member of this set. The second condition is that if you pick any two elements, x and y, from the set S, then their sum must also be in S. That means that S must be closed under addition. S must be closed under addition. That means you pick any two elements in S and add them. The sum should be S. Then the last condition is closure under scalar multiplication. That means if I were to pick a scalar alpha and multiply by x, x is a member of S, and alpha is the n scalar, this product should be in S. Remember here that S and Y, X and Y are in S, and alpha is a scalar. It's any scalar or any integer. Now, these three are the conditions that must be fulfilled by S for S to be a vector subspace. So let's see which of these, because the question is which of the following are subspaces. So I want to see which of these three meets these three conditions. Which of these four meets these three conditions? Let's begin with the first. Now, the first one, from even just looking at it, I can see it's a vector subspace. We've been told that this, let me call it vector, let me call it subset A, and the subset A is given to us as a set consisting of elements X, Y, Z in R3, such that X plus 2Y will be 3Z. So we are not given another condition that must be met by the elements X, Y, and Z, other than that the sum of the first element plus 2 times the second element should give you 3 times the third element. That's the only condition that we are given. Supposing X is 0, then we would have 0 plus, and supposing there's also another 0, Y is 0, then we would have plus 2, 0, and this would be, is in fact the same as 3. So 0 plus 2, 0 plus 3, 0, now is equals to 3, 0. That means, this implies that 0, 0, 0 is in S, as in A. I said that let that vector be called S. So that means this vector has 0, 0, 0. So that means the first condition is met. It means that this A meets the first condition, that it has the 0 vector. Now let's see whether it meets the second condition. The second condition, we want to see whether it fulfills closure by addition. So supposing I have vector B, which is E, F, G, and vector G, oh no, not G, let me use something else. Use H. Vector H, which is N M K. Supposing I have that, what I want to show is what would be P plus H. P plus H would be E plus N F plus M and G plus K. Now, but we have been given a formula here. We've been given a formula that the sum of the first two is X plus 2Y should give you 3Z. Just create some space here. Create some space. By this formula, what we know is that if I take H for P alone, for P, we know that P plus 2F should give us 3. By this formula, the first element plus 2 times the second element should give you 3, the third element. And then for Q, now for H, for this H, we know that N plus 2M should give us 3K because this P has been picked from air and the H has been picked from air, so they must meet this condition. Now, what about P plus H? What would be P plus H? P plus H we've already shown that is this. So what is the second element? What is the second? First element is E plus N, and then plus 2 multiplied by the second element, which is F plus M. What does this give you? We want to see whether it will give us 3 times the third element. So that's why we've not seen me right here 3 plus this, because I have not ascertained that it will give me 3 times that. Let me see. Let's just open the bracket. It will be E plus N plus 2F plus 3 or 2M. Now bring the elements of F together. Now the elements of P together. The elements of P were E and 2F. E plus 2F. And then the elements of, let me put this one inside the bracket. Put it inside the bracket. And that is plus the elements of H, I want to put them together. And one of H is N plus 2M. Let me clear some space here. Clear some space, just some small space here. I will see what to do here. Now, what was E plus F, 2F? E plus 2F is here, is 3G. What was n plus 2m? N plus 2m is here is 3k. So what is this? This is 3 multiplied by g plus k. And that's what we wanted to show. We wanted to show that the first element, this first element, plus 2 times the second element, will give us 3 times the third element. So that means, what that means, therefore, is that a closure added by addition has been satisfied. That means that P plus H is in S, no, is in vector A, is in set A. So we've shown that A is closed under addition. We want to show that A is also closed under scalar multiplication. So let me just erase this. So I want to pick, well, I still want to use P, which is, let me say it's E, F, G, such that since P has been picked from A, we know that P plus 2 times the second element will give us 3 times the third element. But what I want is to pick a scalar alpha. And I want to multiply this alpha by P. And when I do that, I should be able to get alpha F, alpha E, alpha F, and alpha G. Now, I want to see whether this alpha P will be in A. So for it to be in A, it must fulfill this condition. And that's what I want to find out. What is alpha E plus 2 alpha F? This is the same as I can put alpha outside. Can put alpha outside. And inside the bracket, what I'm saying is E plus 2F. But what is E plus 2F? E plus 2F is 3G. That is alpha times 3G. But if you want to write it as, I should have done this. So that then I just write as 3 alpha G. And you've seen that this condition has been met. That condition has met. So that means that hence A is a vector subspace. Now, if I was to, this question did not ask me to do everything that I've been doing. The question just wanted to say whether it's a subspace or not. But now what I've just done is, supposing I was asked to show that A is a subspace, then you would just have done what I've been doing. If the question would have been show that it's a vector subspace, then we would have gone through the steps that I've just gone through. Now, what about B? Is it a vector subspace or not? Now, if it's not, you just give us one example to show that the conditions, the 3 conditions that I gave are not satisfied. One of the 3 conditions that I gave is not satisfied. I gave the condition that the 0 vector must be in B, that there must be closure, it must be closed under addition, and that the scalar multiplication must also be closed. Now, so I just want to call this as vector, no, set B. Just want to call this set B as the set of PQR such that PQR are greater than or equal to 0. Now I want to say that this set here is not closed under scalar multiplication. For instance, pick negative scalar here. Pick a negative scalar, any negative scalar. Pick any negative scalar. We know that from this definition, B consists of vectors whose entries are non-zero. No, non-negative. Whose entries are non-negative. So those are the vectors. So for example, we could have a vector U which is 1, 1, 3, and this one will be in B. This one will be in B. Because all the entries are non-negative. All the entries here are non-negative. So I've now picked a non-negative scalar, and I want to get this 2U. I want to see what I get. 2U will be negative 2, negative 2, negative 6. And you can see that this is not in B. Because the entries are negative. The entries are negative. So this result here is not in B. And therefore, B here is not closed under scalar multiplication. And so therefore, B here is not a subspace. This one is a subspace. What about C? Let me just take a space and see whether C is a subspace or not. And if it's not, I just give one example to show that one of the conditions is not met. Now, C is a set comprising of 0, A plus 1, such that A is a real number. Now, I can see that this C is not a space. What is my reason? My reason is I want to suppose that C has a 0 vector. Suppose it has a 0 vector. Then this 0 vector will be equal to what I have here is 0, A plus 1. Now, so what is A? Because if I have a 0 vector, then the 0 vector fulfills this condition, must fulfill this condition. What will be A? When I look at the second entries, I find that A is 0. Comparing the second entries, A is 0. What about if I compare the third entry? Third entry, I find that A 0 is A plus 1, which in fact means that A is negative 1. Then that means that this A does not exist, because A cannot be 0 and at the same time be negative 1. So there's no solution, there's no value for A. No value for A. And so this is enough to say that C is not a subspace. Subspace is not a subspace, because it does not have the 0 vector. Because if it were to have a zero vector, then equating this zero vector to this, we would have obtained a value of a single value of a, but the same a cannot have two different values. And therefore, C here is not a vector subspace. Let's look at D. Want to see whether it's a vector subspace or not. From the look of things, let me just write it first of all. D is a set comprising of M, N, K in R3 such that the square of the first element equals the square of the third element. The square of the first element equals the square of the third element. So I can see therefore from the look of things that this will not be a subspace, will not be a subspace, because D consists of vectors whose square of the first entry equals to the square of the third entry. So for instance, some of the vectors here will be like 1, U, which is 1, 0, 1. Since the square of the first entry 1, the same as the square of the third entry 1. The other vector here will be B, vector like -1, just a minute, -1, 0, 1, because I can see that the square of the first entry equals the square of the third entry. So this first entry and the third entry here. But now, what about the sum of these two vectors? Will it be in D? Will it be in D? So let me see. U plus B will be, if I add this, I will have a 0. If I add that, I have a 0. Just adding the corresponding entries, elements, and this will be 2. This is not in D. Is not in D. This is not in D. Because I can see that the square of the first element is not equal to the square of the third element. So it's not in D. And therefore that means that D here is not a vector subspace. So that is how we are supposed to have done this question. Supposing the question was show that the following 3 here are not vector subspaces, then you were to look at the set that is given and give one condition that is not satisfied by use of an example. Let's go to the next question. So the next question is asking us to find the adjoint of this matrix. And we are given 4 options. You have to choose one. But before you choose, you have to calculate. Now, first of all, before you do that, you'll be getting a minor of every element. And then you also get the cofactor of every element. So what I mean here is that we shall get the minor of 1, minor of 2, minor of 3, minor of 4, 0, minor of 5, minor of 3, 0, minor of these 2, minor of these 4, minor of these 3. And then get their corresponding cofactors. To get the cofactor, we just take the minor and multiply by the sign. The sign will be -1 raised to the row plus the column. So the ith row plus the jth column. For example, this element here is in row 1, column 1. So I is 1 and j is 1. This element here is in row 1, column 2. Row 1, column 2. So I is 1 and j is 2. J is 2. So I here stands for the row of the element, and j stands for the column of the element. So let's just write this matrix and then do the question. I create space. Let me move to the space where I'll be working from. Let me rewrite the matrix, and the matrix is here's the matrix. Let me just go back and copy the matrix. The first row has 1, 2, 3. I just write somewhere 1, 2, 3, 0, 5, 0, 2, 4, 3. 1, 2, 3, 0, 5, 0, 2, 4, 3. Just go back now. So our matrix A is given to us as 1, 2, 3, 0, 5, 0, and 2, 4, 3. So I want to get the cofactor. Let me just show you how to get a minor of minor first of all. The minor of 1 is the determinant of the matrix formed when you delete the row of 1 and the column of 1. So when you delete the row of 1, the column of 1, the matrix is left is 0, 5, 0, 4, 3. So this determinant is the minor of 1, or the minor in the position 1, 1. So this minor is just 15, minus 0. What about the cofactor? The cofactor, yes, the minor is 15. And the cofactor in that position would just be -1 raised to the row of 1 is 1, and the column of this element is also 1. So it's -1 raised to 2, which would be positive 1. I multiply this by the minor. Multiply this by the minor. It will just be 15. That's how we get a minor. This is a minor, and this is the cofactor. What about the minor of 2? The minor of 2 is 2 here. I delete its row and its column, and the matrix that is left is 0, 0, and 2, 3. So the minor, therefore, is 0 minus 0, which is here. What about the cofactor? The cofactor will be -1 raised to, the row is row 1, the row of 2 is row 1, and the column of 2 is 2. Then multiply by the minor, but the minor in this case is 0. So this will be -1 raised to 3, which will be -1, times the minor, and the state is 0. So this is how we'll be doing it. But of course, in another video, I told you that the signs of the cofactor will be interchanging, and it will be positive then negative, positive, negative. This positive, negative, positive, negative, positive. This is the negative, positive, negative, positive, negative. So you see, if this is positive, then this is negative. Then this will be positive, and then this will be negative, and so on. And if this is negative, this will be positive, then this will be negative, then this is positive, and so on. And the same thing continues. Now let's answer this question. I want to begin by finding the minus. Then I'll include the signs of the cofactor. So the cofactor matrix, would be, what is the minor of 1? The minor of 1, delete the row and the column of 1, and you have 5, 0, and you have 4, 3. And of course, the sign is positive, so I've just left it. I know it's positive. I'm at 2. The minor of 2, delete the row and the column of 2. The matrix that remains, when I delete, let me just move it close a bit. When I delete the row and the column of 2, the matrix that remains is that. And the 2, 3, this is the minor. This is the determinant is the minor. But now the sign of the cofactor will be positive. Because it's plus, minus, plus, minus, plus, minus, plus, minus, plus. Now, the second element is 3. The sign will be positive. I delete the row of 3 and the column of 3. They have 0, 5. The row of 3 and the column of 0, 5, 2, 4. Let me come to the third element, which is 0. Delete the row of 0 and the column of 0. You have 2, 3 as the remaining matrix. 2, 3, and 4, 3. The sign here was positive, negative, positive. This will be negative. The second element is 5. Delete the row and the column of 5. The row and the column, I have 1, 3. 1, 3, 2, 3. Negative, positive, this will be negative. The second element, the next element is this one, 0. Delete its row and its column. You have 1, 2 as the remaining matrix. And 2, 4. We are at 2 here, this 2. The sign is positive. Delete its row and its column. We have 2, 3. And 5, 0. The sign is negative now. We are at this element 4. It's minor B. It's minor B. Delete its row and its column. With the determinant of the matrix that remains, the determinant of the matrix that remains is 1, 3, and 0, 0. Then finally, the minor of these 3, delete the row and the column. You have 1, 2, and 0, 5. Let's just check that we have the correct signs. Positive, negative, positive, negative, positive, negative, positive, negative, positive. Let me just reduce those brackets. Okay. So what do we get as the cofactor matrix? Just write it here. This will be 15 minus 0, which is 15. This will be 0 minus 0 times this negative, which will be 0. And finally, this will be 0 minus 10, which is negative 10. Negative 10. Just write it properly in your notes. Negative 10, just write it properly in your notes. My space is too small, but it's negative 10 there. Let's come to this, is 6 minus 12, which is negative 6. This is 6 minus 12, which is negative 6. That negative 6 times this negative outside will be positive 6. And this is 3 minus 6. 3 minus 6 will be negative 3. What about this? It's 4 minus 4, which is 0, times this negative, which will be 0. This is 0 minus 15. And this is 0 minus 0. And this is 5 minus 0. And this is the cofactor matrix. So let me just write what you've gotten properly so that in a good space, so that we can use it to get the adjoint, because the question wanted us to find the adjoint. But what we have is the cofactor matrix. So let me create this space. So we just found that the cofactor matrix, we found it to be 15, 0, negative 10. We found it to be 6, negative 3, 0. And we found it to be negative 15, 0, 5. This is the cofactor matrix. Cofactor matrix. And of course, you know that this was, 15 was the minor of the first element. 0 was the minor of the other elements. The minors have no signs. 10 was the minor of the third element, and so on. Now, so what we want to do now is to get the adjoint. And the adjoint of a 3 by 3 matrix is just the transpose of the cofactor matrix. Transpose. And you know what the transpose is of cofactor matrix. So by transpose, we just write in the first row to be the first column. The first row here to be the first column. The second row to be the second column. And the third row to be the third column. So this is the transpose of this matrix. And of course, it's what we call the adjoint. It is the adjoint of matrix A. So once you get this transpose, then what you have is the adjoint of matrix A. That's what the question wanted us to do. So we then move to the next question. Now, this fifth question says, if A is a square matrix of order 3, and the determinant of A is negative 4, find the adjoint of A. This is a very easy question. We know that, given matrix A, the determinant of the adjoint of A, the determinant of the adjoint of A will be given by the determinant of A raised to n minus 1. Here, n is the order of A. N is the order of the matrix A. So that means if you're given a matrix A, then the determinant of that adjoint will be the same as be the same as the determinant of A raised to the order minus 1. So in this case, it would be the determinant of this adjoint would be the determinant of A, which is negative 4. Not you write out the determinant. You write out the determinant. It's negative 4. Raise that to the order, which is 3, minus 1, and that would be 2. 3 minus 1 would be 2. And so the adjoint then would have a determinant of 16. The adjoint will have a determinant of 16. I can show an example. The previous question for what was the matrix? Let me just write the matrix. So the matrix was what was matrix A? Matrix A was 1, 2, 3, and 0, 5, 0, and it was 2, 4, 3. You can go back to the question and see what the matrix was, but I think I captured it correctly. Now, how to get the determinant of this matrix? I showed you so many methods of getting the determinant of matrix. I can even use this other method that I showed you earlier. 0, 5, 0, 2, 4, 3. Just add the first column here. 1, 0, 2, and 2, 5, 4. In the earlier video, I showed you how to find determinant using this method, and I gave you a condition on which type of matrices this method will work and which ones will not. Now, so when I multiply along this column, now this diagonal, I have 15. Along this other diagonal, I have a 0. Along this other diagonal, I have a 0. Then these results subtract the sum of, when I multiply this along this diagonal, I have a 0, plus, along this other diagonal, I have a 0, plus, along this other diagonal, I have 30. So the determinant of this matrix, therefore, is negative 15. What about, so this is bit A. What about the determinant of the adjoint of A? Adjoint of A. So by the method I've just showed you would be the determinant of A. The order of this matrix, this is a 3 by 3 matrix. So it's order 3 minus 1. And this means negative 15 raised to, because the determinant here is negative 15, raised to 2, which would be, is it 2.5? Yeah, it's 2.5. So the determinant of the adjoint is 2.5. Of course, we had gotten the adjoint. You can try and find what its determinant is. We had found that the adjoint of this matrix from the previous example, we had found that the adjoint would be, it was 15, 0, 15, 0, there was a 10, negative 10 here. Yes. This was 6, negative 3, and this one was 0. This was negative 15, this was 0, and this was 5. You can go back to the question 4 and find what the adjoint was, but I think this was our adjoint. Then try and find if this is the determinant. Let's see. Let's just arrange this. This will be 15, 6, negative 15, 0, negative 3, 0, and this is negative 10, negative 10, 0, 5. Add the first two columns here, 15, 0, negative 10, and this is 6, negative 3, and 0. Along this diagonal, you have 15 times negative 3 times 15 times negative 3 times 5. Plus, this will be 0, and that will be 0. This will be 0, and that will be 0. Then minus, along this other diagonal, we have a 0 here, plus a 0 here. Then plus, this would be negative 10 times negative 3 and times negative 15. And I think when you do this, you get the same answer as this. So that means if I'm given a matrix, I can get, if I'm given a matrix and it's a determinant, I can get the determinant of the adjoint by just getting the determinant of this matrix and raise it to n minus 1, where n is the order of matrix n. Let's look at the next question. The next question we had asked that if A is an invertible matrix of order 2, then the determinant of A inverse will be equal to. So this is we have the determinant. We want to get the determinant of A, of the inverse of A, and the question is saying that we should choose one of these. But before that, then we supposed to do it first of all and see whether what do we get? Do we get that to be same as the determinant of A, or this, or 0, or 1, or the transpose? Now, but what we know is this. What we know from our basic mathematics is that if you have matrix A multiplied by its inverse, the answer will be identity matrix. The answer will be identity matrix. We also know this, we know this. We know this. We also know that if matrix A, if A is invertible, we know that if A is invertible, then its determinant is not equal to 0. We know that. If it's invertible, then its determinant is not equal to 0. Now let's come back to this equation star and use it. Take a determinant on both sides, in both sides of star. So if I'm getting a determinant on both sides, this is what I would have. And we know what I is. I is the identity matrix. It's like this. If it's a 2 by 2 matrix, then it's this matrix. And I know that this determinant, if I was to get the determinant of I, this I, it just be 1. This minus that would be 1. So the left side can be expanded to mean, I can expand the left side to be the determinant of A multiplied by the determinant of A inverse. And the right side is already saying that the determinant of I will be 1. Now what I want to get is the determinant of A inverse. That means I divide on both sides by the determinant of A. So I would have 1 out of the determinant of A. And of course, we've already said that the determinant of A is not 0. So that means this division is possible, because we should not divide by 0. So this division is possible. So what this means, therefore, is that the determinant of the inverse of A is the same as 1 divided by the determinant of A. Or, as the question has put it, is that the determinant of A inverse is the same as 1 divided by determinant of n. So that means that my answer then will be C. My answer is C. And I've just used a very simple thing that we learned in our basic mathematics. Let's look at the next question. The next question says, find the minor of element in the second row, third column. The second row, row 1, row 2. This second row. Third column is 1, 2, 3. So we want the minor of this element. Second row, third column. So the minor will be the determinant of the matrix that remains when you delete the row of that element. When you delete second row and third column, the matrix that remains is 2, -3, and 1, 5. So this is 10 minus 3, which is 13. So that is the minor. That is how we do the minor. And I had shown you in an earlier question how to do that. Now we are asked to find the determinant of this matrix. Now, once you know to get the determinant of a matrix, you can get of any matrix, whether we had trigonometric functions here or logarithmic functions here. You can still get. For somebody can write here cos 45, or sin 45, tan 45, cos 40, and so on, and ask you to find the determinant of a matrix. Once you have the knowledge of finding the determinant, you should do that. Now, this one is between logarithmic functions, and we learned how to do these kind of functions, how to simplify them in our earlier mathematics. Let's just do it. So the determinant of this matrix will be the product along this diagonal, which is the logarithm of 512 to base 3 times the logarithm of 9 to base 4, and then this result, subtract from it, along this diagonal, we have the logarithm of 8 to base 3 times the logarithm of 3 to base 4. Now, it's good to always try and work with the same bases. Because I can see the base is 3, the base is 4, the base is 3, and the base is 4. So for this one, it's easy. For this one, it's easy to work with the same base. Now, what about for this one? It's also very easy. So let's try and simplify. 512. Just want to write it as a product of prime factors. I want to use 2. So 2 go here, 256 times. I think so. It's 256. 2 goes here twice, remains 1, into 12, into 11, 5. And into the main one again, into 12 to be 6. So what about 2 here? To be 1, and into 2, 552, 8. And then 2 now becoming easier. 6, 4, yes. And then 2 to be 32. And then 2 to be 16. And then 2 to be 8. Then 2 to be 4. Then 2 to be 2. Then 2 to be 1. Yeah. So that means this can be written as the log of 2 raised to what? 1, 2, 3, 4, 5, 6, 7, 8, 9. To base 3 times the log of 4, and the log of 9, let me call it 3 raised to 2 to base 4, What about this one? This one is log of 2 raised to 3 to base 3, because 8 is 2 raised to 5, followed by log of 3 to base 4. Now, using laws of logarithm, we know that this one can be written as 9 multiplied by log of 2 to base 3, and this can be written as 2 log of 3 to base 4 minus, this can be written as 3 log of 2 to base, this is 2, huh? Log of what? 2 to base 2, because this is 1 here, this is 1, was it 2? That was the base 2. Let's see, what was it? And this, the base was 3. The base was 3. The base was 3. Yeah, the base was 9. We almost lost it because this was becoming 1. Then times the log of 3 to base 4. Now, we now want to make the bases be same. And to make the base be the same, there's something we know. Under laws of logarithm, we know that if you are given log of a to base b, this can be the same as 1 out of log of b to base a. So if I were to change the bases, this is how I change the bases. This is how I change the bases. So I want to change these bases. You can see this is 3 and this is 4. So, but these are 3 here. On this 3 to come and the 4 to go there. And you can also see the same thing here. There's a base of 3 and a base of 4 here. But there's a 3 here. Want this 3 to come here and 4 to go there. And these ones you learn under logarithms. You don't learn them under linear algebra. The only thing you learn in linear algebra is how to find the determinants, and that's what I'm showing. But these laws of logarithms, we needed to have learned them earlier in the basic mathematics. So let me create some space. And remember this law here that I'm erasing. So let's create space. I just have to create this and leave the last step there so that we use it. Now, so I want to change bases here. So what I have there is 9. Let's write it properly. I have a 9. I want to maintain this base, log of 2 to base 3, but I want to interchange this base. So it would be 2 out of log of 4 to base 3. Remember what I just said? What I just said is that if I'm given log of a to base b, this is the same as 1 out of log of b to base 4. So that's what I did here. This part here is the same as 1 out of log of 4 to base 3. But there's a 2 in the numerator, so I get this. Then minus, want to change this base, 3 log of 2 to base 3 multiplied by 1 out of log of 4 to base 3. Yes, I just think that's the best problem. Now, of course, I can see something here. I can see that 4 here can be written as 2 raised to 2. 4 can be written as 2 raised to 2. And the same 4 here also can be written as 2 raised to 2. So what do I have? I have 9 log of 2 to base 3 times 2 out of 2 log of 2 to base 3. And I know that you know how I got this. Yeah, I got it. This is how I got it. I have log of 4 to base 3, but this is same as log of 2 raised to 2 base 3. And using law of logarithm, we know that this one comes. That's what happened. That's what happened. You can see 2 has come here. This power here has come. I do not require what is at the bottom, so let me just remove it because we already have written what we want. Minus 3 log of 2 to base 3, and this one can also be rewritten as 1 out of 2 log of 2 to base 3. Now you can see that these 2 can cancel that. And you can see here I have log of 2 to base 3 and log of 2 to base 3 in the denominator. So you can see that I'm left with 9 at this point. I'm left with 9 in this bracket. You can see that I'm left with a 9 bracket. These are the brackets. What I see, you're seeing that this is in the denominator and this is in the numerator. So I'm left with 3 out of 2, which becomes 18 minus 3, which is 15 out of 2. And that is the answer that you're supposed to have chosen. Part A was 15 out of 2. Now this question, you're given A and you're given the inverse of B, and you're asked to compute A, B, the inverse of that. I have seen in some books a theorem that it says that this will be the same as A inverse multiplied by B inverse. Maybe you try and see whether that will give you the same answer as the one I get. But for me, I'll not do this. That theorem, it says A, B, the inverse of that will be the same as that. But I really doubt if they're the same for matrices. For matrices, I don't know whether it will be the same. Maybe I will try later. But I still believe that it will give you a different answer. So what I'll do, therefore, is not this. What I'll do, I'll get B out of B inverse and just do what the question has said. A times B. So I get B out of B inverse. So of course, I know that if I'm given B inverse, if I get the inverse of this inverse, what I find is B. So how do I get B? I get B by finding the inverse of B inverse. So by finding the inverse of B inverse, I get B. That's what I do. So after getting this B, I'll multiply it by A. The product of AB, I get the inverse of that. That's what the question asks. So those are the steps I'll be using. So let me just note down the matrix and then use it. The matrix B is not B inverse. Matrix B inverse is 1, 2, 0, 0, 3, negative 1, 1, 0, 2. 1 to get B. So as I said, I've been given B inverse. So I need B. B will be the same as the inverse of B inverse. So what is B inverse? B inverse has been given to us as it is 1, 0, 2, 1, 2, 0, and 0, 3, negative 1, and then we have 1, 0, 2, 1, 0, 2. So this is B inverse. For me to get the inverse of this, I need, okay, so I need B, which is the inverse of this matrix. 1, 2, 0, 0, 3, negative 1, 1, 0, 2. So B should be the inverse of this. So first of all, I get the determinant of this matrix. The determinant of this matrix 1, 2, 0, 0, 3, negative 1, 1, 0, 2. And you know how to find the determinant of matrix. I showed you various ways. When you do this, you get this determinant to be 4. After getting the determinant of this matrix, I want the cofactor matrix. Cofactor matrix of this. So I don't know whether I should do it again because I've already showed you how to find a cofactor matrix. That it would be, I'll just show you two things. I'll just show you for the first line, then I just write the answer. Then you continue to find it for the other elements. Now for the first line, the cofactor of this element, delete its row and its column, I have 3, negative 1, and 0, 2. So the determinant of this. Then the second element will be negative. The other side will be negative. Delete the row of the second element and the column of the second element. You have 0, negative 1, and 1, 2. And then the third element here is 0. The sign will be positive. Delete its row and its column. You have 0, 3, and 1, 0. Let me just do it for all of them, actually. Like just the other element here is 0 here. Delete its row and its column. You have, but try and be accurate because I'm fast. I don't know whether I'm accurate, but just delete this row and the column. The 8 and 2, 0, and then 0, 2. And then for the other elements, the other element is 3 here. Delete its row and its column. I have, I'll come back and indicate the signs. Delete its row and its column. I have 1, 0, and 1, 2. This other one, delete the row of negative 1 and the column of negative 1. You have 1, 2, and 1, 0. This vertical lines mean determinant. Come to this last row, element 1 here, delete its row and its column. You have 3, 0, and 3, negative 1. And this other element is 0 here, delete its row and its column. You have 1, 0, and 0, negative 1. And lastly, these other elements, delete the row and the column. You have 1, 2, and 0, 3. Let's indicate the signs. Positive, negative, positive, negative, positive, negative, positive, negative. The first one here gives you 6 minus 0. This other one gives you 0 minus 1, which is 1, then times this minus the negative 1. Negative 1, and this other one will give you 0 minus 3. I'll write it properly. I know here it's not visible because the space here, but it's 3 there. Okay, for this other one, it is 4, but there's a negative outside. And for this other one, it's 2. And this one is 0 minus 2. And there's a minus outside that becomes positive 2. And this is negative 2. Negative 2. And this is negative 1. There's a minus outside. Becomes positive 1. And this is 3. Close the bracket. So let me just write properly here what my cofactor matrix is. So my cofactor matrix I've just found 6, negative 1, negative 3, negative 4, 2, 2, and I found negative 2, 1, 3. So I hope this is now visible. Now that we have the cofactor matrix, what follows is the adjoint. And I know that the inverse of the matrix A, B, now our matrix B now, which is the inverse. The inverse will be given by 1 over determinant times the adjoint. Times the adjoint of B inverse. 1 over our determinant was 4. And the adjoint, we write the transpose of this matrix, which is 6, negative 1, negative 3, negative 4, 2, 2, negative 2, 1, 3. So this is our B. Because what is the inverse of B inverse? That was to give us B. So our B is this. Now we have our A, so we need to multiply A and B and then get the inverse of that product. So what is AB? AB, therefore, let me write this constant here. It has no harm writing this constant outside. Then I write A. What was A? A was 1, 1, 2, 0, 2, negative 3. And then 3, negative 2, 4. And our B is here. 6, negative 4, negative 2, negative 1, 2, 1, negative 3, 2, 3. Of course, negative a quarter is already outside. So when I multiply this, you can deduce later. What do you get? I was getting just then maintain my quarter here. Maintain my quarter and then just multiply these matrices. And so that was giving me negative 1, 2, 5, 7, negative 2, and negative 7. And then 8, negative 8, 4. This is my AB. But now to get the inverse of AB, the inverse of this product, I must take my quarter inside. I must take my quarter inside. And so this is negative 1 out of 4. A half, 5 out of 4, 7 out of 4, negative a half, negative 7 out of 4, then here it just be 2, negative 2, and 1. This must get the inverse. So a quarter must must be included in this matrix. You don't leave it outside when you get the inverse. Now, at this point, I'll not do what you're supposed to do. I'll just tell you, of course, you now get the inverse of matrix. And if you don't know, I had already given a video on how to find the inverse of a matrix. So what you need to do, there are various ways. You can use row reduction, one of the methods that I showed you, or you can use, first of all, find the determinant of this product. Determinant. And if you do that, I got the determinant. Did I use the determinant? Yes, I used the determinant, and it was negative 19 out of 4. And then proceed with the cofactor method. Get the cofactor matrix. Then get the adjoint of this matrix, and then the inverse. And when you do that, you'll find the inverse as the final answer. You find it to be, let me just write it properly here, where there's enough space. But you've understood those steps, that once you reach here, you have various methods you can want to use. All of them I've showed in my videos. You can use row reduction method. Or if you don't want that, then you can use the one of the adjoint. Where you have the determinant first of all, and then get the cofactor, and then get the adjoint. Then 1 over determinant times the adjoint gives you the inverse. And so I was getting my inverse, which is my final answer, as 16 out of 19, 12 out of 19, 1 out of 19, 21 out of 19, 11 out of 19, negative 7 out of 19, 10 out of 19, negative 2 out of 19, and 3 out of 19. Of course, you can even factor 1 out of 19 outside if you want. If you want, you can factor it out and just write 16, 12, 1, 21, 10, negative 7, 10, negative 2, and 3. And that becomes the answer. And I think that is the format that the question wanted. The question wanted the 1 over 19 outside. We have so many methods of solving simultaneous equations, and I've shown all of them in my videos. One, you can reduce the system to echelon form. Reduce to echelon form. And this method is called Gaussian elimination. You can use Gaussian elimination. The other method you can use is by transforming the system to reduced row echelon form. Reduced row echelon form. Or the method of using would be Gauss-Jordan elimination. Of course, I also showed you Cramer's rule. Cramer's rule as another method of solving system linear equations. And I've showed you the method of use of inverses. Use of inverses. I also showed you that, where you find the inverse of this matrix and multiply the inverse on both sides. Multiply here by the inverse of this matrix and here by the inverse of this matrix, and you have the answer. So this question was open. You were to use any of the methods. I choose to use the one of Gaussian elimination, or should I use the one of Gauss-Jordan? Whichever method, but let me use Gauss-Jordan elimination. I want to reduce this, transform the system to this augmented matrix. I want to transform it to reduced raw echelon form. And you know how to do this? Transform to reduced raw echelon form. When you do that, what you get, I'll just write the final results, and you can do later. The final result will be 1, 0, 0, 0, 1, 0, 0, 0, 1, and this will be 0, 2, negative 1. So what this means that x is 0, y is 2, and z is negative 1. But the question was solved. So when you are solving, you're giving a solution. So the solution, this system has one solution, and that solution is 0, 2, negative 1. This is the solution to this system. Although the question was find the value of x, y, and z. After you finding x, y, and z, you write the solution. Also, the solution is this. This system has a unique solution, just one. And here it is. Now, on your own time, try to transform this matrix and see that you obtain this. Or if you want, you can also use, you can transform it to, you can reduce it to echelon form. And what will we get? Let me just write the final result. If I was to reduce to echelon form, this is what I would get. Just write the final result. Reducing to echelon form. So you choose any method you want. But as an assignment, I ask you again to reduce this to echelon form and see that you get this 3, 1, negative 2. What I get 0, 7 out of 3. Try and see that you get this 7 out of 3, and then this was 4, this was 7 out of 3, and this is 0, 0, 5, negative 5. So this is what you get if you have to reduce to echelon form. Reduce to echelon form. Of course, there are so many steps here involved, and so I leave that to you as assignment because you already know how to do that. When you do this, then it means that this, you look at the last question here, the last row here, it means 5z is negative 5, which implies that z is negative 1. Then you solve going up from the bottom going up. Come to this other equation. Of course, this row, 7 out of 3 is common, so what we have there is y plus z is 1. When I multiply through by 3 out of 7, I would have 1, 1, 1. So it's y, z is equals to 1. But z, we know it. It is negative 1. So negative 1 crossing this side, it means y is 2. And then proceed and find x. We'll find x to be 0. And write the solution. Solution is 0, 2, negative 1. 0, 2, negative 1 is the solution. Now, this question says, find the condition for the universe to exist. For this universe to exist, find the condition. So we know that for the universe to exist, the determinant of the matrix should not be equal to 0. That's what I'll do. That the determinant of this A should not be equal to 0. So that's what I do. I just find the determinant of this matrix. And I know that this determinant should not be equal to 0. Now, I can find the determinant by making my work easier. I can say I have a 0 here, so I may want to get another 0 along this column or along this row so that my work is easier. I choose to make a 0 along this column. I want to get a 0 in this position. So what I want to do, I want to subtract, I want to take row 1. I want to get the new row 1 by taking the current row 1 minus 2 row 3. Current row 1 minus 2 row 3, what does that give me? So if I multiply this by 2 and subtract from that, I have a 0. If I multiply this by 2 and subtract from that, I have k minus 2. If I multiply this by 2, I have 6. From this, I have negative 9. Yes. Then this other one remains where it is. It remains where it is. Then this other one I also leave it where it is. And this determinant should not be equal to 0. Now what do I have? I want to get determinant along this row, this column. I know it to be 0 times, and I know that anything multiplied by 0 would be 0. So it will be times the determinant that is left when you delete this row and this row. So it will be 2, 5, 1, 3. But since I have a 0 here, I would have 0. Everything would be 0. And again, this other 0 times the determinant that is left when you delete this row and that column, k minus 2. And again, the whole thing there will be 0. So the only thing that it will work is this one. Remember, I'm doing it along this column. So 1 times the determinant of the matrix that remains when I delete a row of 1 and the column of 1. It's k minus 2 minus 9 to 5. The other ones are not important because this will be 0. Because I multiply by 0, multiply by 0. So the rest here will be 0. Let me just delete it. They're not important. I only put them here to show you that I'm doing along the first column. Otherwise, they're not important. So there was a 1 here. And this should not be equal to 0. Now, what is this? This is 5k minus 10, and then plus 18. Because it will be minus 18. This should not be equal to 0. So you can find k here. You can find k. Because what I have here is 5k. I want to take that on the other side of the equal sign. And what am I taking there? I'm taking the negative 8. Negative 8, because this is 8. So I'm taking the negative 8. So that k, therefore, should not be equal to negative 8 divided by 5. Or k should not be equal to negative 1.6. So you see, it's very easy once you understand what it means. When I understood that for the inverse to exist, the determinant should not be equal to 0, and I just wrote it, and I've been moving with it, I already found that k should not be equal to negative 1.5 for this inverse to exist. Let's move to the other question. And look at this question 12. We are given matrix A, and we are told that find the value of mu such that A plus mu I, where I is the identity matrix, that finds mu such that this is singular. So what we know that a matrix is singular if its determinant is 0. So that is what we shall be using. So what is mu I? Mu I is just mu times the identity matrix. This is supposed to be 0, 1, 0. 0, 1, 0, 0, 0, 1. So when you multiply that, what you get will be U 0, 0, 0, U 0, 0, 0, U. So what about if you add this to A? So what will be A plus mu I? So this would be negative 4 plus mu, and then 0 plus that would be negative 4, 0 plus that would be 4. About here, we have negative 1 plus 0, 0 plus mu, and then 1 plus 0. And then we will have negative 7. This will be negative 6 plus 0. And this will be 7 plus mu. So when this determinant, the determinant of this is singular, that means this determinant must be 0. So let's just now do the question. Just equate this determinant to 0 and find mu. So this is the matrix. Determinant of negative 4 plus mu, negative 4, 4, negative 1, mu 1, negative 7, negative 6, 7 plus mu. Want this determinant to be 0. Now I think of ways of making my work easier because I'm finding determinants. One may choose the longest way, but I want to choose the shortest way by making my work easier. I want to create zeros in a longer row or a longer column, as many as I can. Now, for instance, if I want to get column 1, and I'm taking the current column 1 plus column 3. The current column 1 plus column 3, what does that give me? That will give me this 4 plus that will be 0, so I have mu there. This negative 1 plus this 1, I have a 0 there. And this negative 7 plus this 7 plus mu, I will have a mu there. Okay. I'm just adding column 1 to column 3 to column 1. So this gives me mu, that gives me 0, that gives me mu. And I write this column 2 the way it is. Column 2, I write it the way it is. And column 4, I write the way it is. So I've already created a 0 here. So I think of creating another 0. I may choose to create it here. At this point, by just subtracting row 1 from row 3. But I may want to place it here. So whichever place, let me put it here. Let me put a 0. So I just want to create this space. And if you have a book, that means you're following, you can write what I'm doing. Because for me, I have a very limited space. I have to delete from time to time. So I have the current row 3. No, yeah, row 3. This time is row 3. It was column the other time. So I'm now doing the row 3. The current row 3, no, the new row 3, I want it to be the current row 3 minus row 1. When that happens, row 1 remains where it is. Row 1 remains where it is. I want this to be 0. Row 2 remains where it is. But what about this row 3? I'm subtracting row 1 from row 3, so this becomes 0. This minus that becomes negative 2. Because it's negative 6 minus 4. And this will be 3 plus mu. Let me create some space. I'm now in a position to find the determinant along the first column, along this column. And you see how 0 makes my work easier, because I would have taken this times the determinant that is of the matrix that remains plus this and times the matrix that remains and so on. So when I delete the row and the column of u, I have u minus 1. No, just a minute. It's u and 1, negative 2, and 3 plus 2. This should be 0. Now, this is same as this. Multiply that, I have u square plus 3u minus 2, which is plus 2. And this should be equal to 0. So what this means is that u is 0. U is 0, or u square plus 3u plus 2 is also 0. This last equation can be factorized as u is it plus 3, because the values here, the values that you multiply and get 2, the product is 2, and the sum is 3. Those values are 2 and 1, 2 and 1. So when you factorize that, you would have what I've written there is not correct. So you would have them just delete this, because the two values whose product is 2 and the sum is 3. Those two values are 1 and 2. So what happens when you factorize? When you factorize, you would have u plus 1, u plus 2 is equal to 0, which implies that u is negative 1 and u is negative 2. But you already had found another u to be 0. So we can call them u1, u2, u3. But the values are negative 1, negative 2, and 0. This question is similar to the ones we've done before. The determinant is 0, find the value of k. So let's just do that. Let's just equate this determinant to 0 and see what we get. Equate to 0. And look for easier ways that you can make this easier. I want to begin by getting a 0 in this this position by just adding row 2 to row 3. So my new row 3, I just want to take the current row 3 plus row 2 and see what to get, what I get. So let this remains the way it is, to remain, that remain, 4 minus k, and then 1. Just want to add this to that ourselves. Add this to that to have negative k. Yes, just adding this to that, then add this to that to have negative k again. Is equals to 0. And I think of another way of introducing a 0. Now that I have a 0 here, I may think of introducing a 0 in this column or in this row. Let me introduce it here in this row here at this point. I can see that if I was to subtract this column from this column, I would have a 0. I'm just subtracting negative k. For instance, what I'm talking of, negative k minus k would be negative k plus 3, and they have a 0 at this point. So it's just upon you now thinking. This is a question that requires you to think of how to make it easier. Otherwise, you would choose the other way that is longer, finding the determinant, and it will be longer for you. Although it will still give you the answer, but it will be longer. Now, so the next step that I've said I'm taking, I want column. I want column 2. And I'm taking the current column 2, then minus column 3. So what does this give me? Let me see. Of course, column 1 remains what it is. Column 2, I'm subtracting 2 from 2, I have a 0. I'm subtracting 1 from this, I have 3 minus k. And I'm subtracting this from this, I have a 0. Because it will be negative k minus k. And that will give us 0 there. This will be 0. That's how I work it out. And then column 3 remains the way it is. Now I can now get my determinants along this row. Along this row. Remember, it was positive, negative, positive, negative, positive. If I was to the other sides. So let me create some space. So it's positive, negative, positive, negative, positive. So it's positive k into, when I delete the row of k, negative k, and the column of negative k, I'm left with the k minus, now 3 minus k, 0. And I'm left with the 2, 3 minus k. Oh, this determinant was to be 0. Was to be 0. Now, so what is this? What I have here is negative k multiplied by, this is 9. We just write it as 3 minus k, 3 minus k, because in fact this is 0, so there's no need. And I put this to 0. When I do that, it's either negative k is 0, which implies that k is 0, or 3 minus k is 0, which implies that k is 3. So k is either 0 or 3. Let's look at the next question. Yeah, we already know to find the inverse of matrix. I want to use the method of the cofactor, the same way down. So that means I'm answering question A. That means we begin by finding the determinant of M. And in order to do that, what I find, I just write the answer. The determinant of M I found to be negative 24. You can use any of the methods. Then find the cofactor matrix. Cofactor matrix. After finding the cofactor matrix, find the adjoint. Find the adjoint matrix, which is of course the transpose of the cofactor. Then after that, find the inverse M. Find the inverse of M. And what will you find? You'll find this thing, only that A will be 0. When you do it, A will be 0. A will be 0. And C will be 4. C will be 4. And B will be 2. B will be 2. When you do it, you find out. Of course, you're doing this and then factor out what is common. Factor out 1/12 will be common. Factor out and then you B will be 2, A will be 0, and C will be 4. So you have the inverse now. And once you find the inverse, the question asks you to find question B. And now answer question B. Question A, I know you will follow those steps and find the inverse. What is question B? Once you have the inverse, which is 1 out of 12 into 3, 3, 0, 2, negative 4, negative 2, negative 1, negative 1, 4. Just multiply this by what you have here. This, what you have there. And what you get will be x, y, z. What you get will be x, y, z. So when I multiply this, what do I get? I got x to be 2, y to be negative 1, and z to be 3. So just multiply this. Just multiply this matrix, and you get it. Let's look at this question. Just using the properties of the determinants again. I'm looking at this, and I'm seeing there's some similarity between second row and the third row. There's some similarity there, so I can create a 0. Because every time I'm doing this, I'm thinking of how do I make my work easier by creating zeros either along a column or along a row. So what I want to do is, I'm taking row 3. I'm taking row 3, the current row 3. Now, the new row 3, I want to get it by taking the current row 3 minus 2 row 2. So when I do this, what do I get? I've not touched row 1. I've not touched row 2. But I've multiplied row 2 by 2 and subtracted the result from row 3. So this by 2, subtract from this, you have 0. This by 2, subtract from this, you have 0. This by 2, subtract from this, you have negative x. So this is plus, minus, plus, minus, plus. So it's negative x into the determinant of the matrix that remains when I delete the row of negative x and the column of negative x. It is x plus y, x, then 5x plus 4y, and this is 4x. So I delete the row and the column. So what do I get here? This is the same as negative x into what? Multiply this, you have 4x squared plus 4xy minus 5x squared minus 4xy. And what do I have? I have negative x. Inside this bracket, I can see I have some similar things, like this and that gives us 0, and this and that gives us negative x squared. When I multiply this, I have x cubed. But that is, x cubed becomes the determinant of this matrix, x cubed. So let's look at the next question. This the method has been specified to us. It was Jordan reduction. So let's just reduce this matrix to transform it to reduce to regular form. And the augmented matrix is 1, 3, 2, 2, 2, 7, 7, negative 1, 2, 5, 2, 7. We now to do this, when you transform it to reduce the regular form, you get the following. You get 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, and here you get 3, 2, 3, 1, negative 2. So what is the question? The question wants us to find EFG. EFG, that is 2, negative 2, 1, negative 2. 2, 1, negative 2. And of course, these are the values of x, y, and z. These are the values of x, y, and z. Let's look at the next question. Find the value of k for the following system to be inconsistent. Now, there are two ways that I will be doing this question. The first way is by use of a determinant. We know that if a system is consistent system, the determinant will be non-zero. The determinant will be non-zero. But the inconsistent system, the determinant will be 0. So I want to use that knowledge, get this determinant equal to 0, and I'll get the value of k. Then I'll show another way, which you know. Now, so let me write the matrix 1, 1, 2, negative 3, 0, 0, k plus 3, 2k plus 1, 0, 1. So this determinant, if it is 0, then this system will be inconsistent. We'll have no solution, because you know that if you're using the method of adjoint to get the inverse, it will be adjoint of a determinant. So if the determinant is 0, then there'll be no inverse. So once there's no inverse, then the system would have no solution. Now, so I'm thinking of a very easy way of getting these determinants. Of course, I already have a 0. I already have zeros. I already have zeros. So if I already have zeros, I can find it along this row 3, can find row 2, can find along row 2. Plus, minus, plus, minus. So it will minus k plus 3. Then delete the row and the column of k plus 3. The row and the column. So I have 1, 2. And I have 2k plus 1. And 0. So this should be 0. So what do I have? I have negative k plus 3 multiplied by, this is 0, minus this. What is this? Minus 4k minus 2. This should be 0. But I wanted the value of k. Then I can divide through by negative. So what I'm left with k minus 3. Then negative k, 4k minus 2 should be 0. So what I have here is k minus 3 is 0, implying that k is 3. Or I also have negative 4k minus 2 is equals to 0, which implies that negative 4k is 2, or that k is negative 1/2. So those are the two values of k that will make this system inconsistent. If k is negative a half, the system will be inconsistent. And if k is 3, the system will be inconsistent. That is one way of doing this question. The other way of doing this question is by reducing this system to echelon form. And let's just see. Of course, I can interchange these two questions. Equation 1 and equation 3. So equation 2 and equation 3 can interchange. So what I have here is x plus 2y minus 3z is 1. I want to interchange equation 2 and equation 3. Equation 3, I have 2k plus 1 x 0y plus z is 0. And this one is 0x, 0y. And what I have here is k plus 3 z is 3. So I just want to look at this last equation. This last equation implies, now what I have for the last equation is k plus 3 is equals to 3. Supposing I did not have x, y, and z, supposing I'm using a matrix, then the last row here would mean that. Okay, let me just put even z. It's no problem. Now, for this system to be inconsistent, it means the value here should be 0. So that I have 0 z is equals to 3. Remember the first question and the second question when we talked about the nature of the system. And there was unique solution, the nature of solutions of a system. There are unique solution, infinitely many solutions, and no solution. So if the value inside the bracket is 0, then this system will have no solution. That's what we want. Once the value of k, so that this system has no solution, is inconsistent, so that this system has no solution. So if the value on the left side is 0, and the value on the right side is non-zero, just as I explained in the first question, this system would be inconsistent. So what will make this value to be 0? What will make this value to be 0 is when k is negative 3. When k is negative 3, I would have 0z is equals to 3, which is impossible. So the system would have no solution when k is negative 3. Now, what about the other value? So I ignore the first two equations. Let me ignore the last equation and just concentrate on the first two. Let me concentrate on the first two. Of course, we've already shown that when k is negative 3, the system will be consistent. So I want to see if there's another value. I want to create a 0 here using this value. So what I want to take the second equation minus, supposing if we are using matrices, we would have talked of second row. So I want to take to get the second row, I want to take the current second row minus 2k plus 1 multiplied by row 1. So that row 1 remains where it is. If I multiply this by 2k plus 1 and subtract from row 2, I'm multiplying 2k plus 1 by row this x, and then subtract the result from this row 2. I will have a 0 at this point. What about here? Multiply this by 2k plus 1. And subtract from here. I will have 2 into 2k plus 1 y minus, because there is 0 y. So multiply this by 2k plus 1, subtract from this. So I would have this is what I would have. Then this one again, I have z 1z, and this one times 2k plus 1. Is a minus, that's why I'm putting plus, because I'm supposed to subtract. So this will be 6k. Oh, I had already put a 3. There, so let me just remove it. But I will make our work easier and fast. 6k plus 3. Then outside the brackets, outside the equal sign, would have something there. I don't have space, but let me write it here. I'm only listen by 2k plus 1 and separate from this, so I have minus 2k plus 1. I can write these things properly. Create some space now. Just hoping that I was accurate when doing this, so that I do not do it again. So this is x plus 2y minus 3z is 1. This is negative 2 into 2k plus 1 y, and this is 4 plus 6k z, because z is equals to negative into 2k plus 1. I want to make this one 1. Which means I must multiply, divide it by whatever is the coefficient of y. Must divide the entire equation by coefficient of y, the coefficient of this y. And the coefficient of y, you can see it's negative 2 into 2k plus 1. So what do we have now? The first equation remains. The second equation, dividing this by this coefficient, I will have 1. Divide this by the same coefficient. What will I have? Let me just divide it somewhere. I have 4 plus 6k divided by negative 2 into 2k plus 1. What will happen if I factorize the numerator? No, you can't. We don't need even to factorize it. There's no need. So let's just write what we get. 4 plus 6k out of negative 2 into 2k plus 1 is equals to, and this one we have negative 2k plus 1 divided by that coefficient, which is negative 2 into 2k plus 1. Of course, this one is a bit easier. We can do it to get negative a half. But now the condition we are looking for is here, because this one cancels here. So the right side, in fact, the right side remains as a half. The right side remains as a half, so I can remove even this. I can remove this and write a half. So the question is, what should K be so that this system has no solution? And I'm just looking at this point, and I'm seeing that for K to be 0, for this denominator to be 0, because once the denominator is 0, because I can even simplify this. Negative 2 can cancel out. Negative 2 can cancel out. Let me just even do that. Negative 2 can cancel out. And when it cancels out, what becomes here? This becomes negative 2. And this becomes negative 3. Let me just delete. Although it's not necessary. Negative 2. I don't know whether I remember what was there. But I think it was negative 3. No, negative 2. Negative 3K. I don't know whether it was that, but there's no problem. My problem is here. Once this determinant is 0, once this denominator is 0, this system would have no solution. Once this denominator is 0, the system would have no solution. When does this denominator become 0? When K is negative a half. Because when K is negative a half, then you have 2 times negative a half plus 1, which is 0. So when K is negative a half, the denominator here will be 0. So, and once the denominator will be 0, a number divided by 0 does not exist. They are very huge now. So K also will not exist. No, K will be, if K is negative a half, the system will be inconsistent. So we found the two values of K. The other one, I don't know whether it was positive 3 or negative 10. Just go through the workings. Find the determinant of a raised to 5. Now, very fast, I know that the determinant of a raised to n is the same as the determinant of a raised to n. That means the determinant of a raised to 5 is the same as the determinant of matrix A n raised to 5. Now, one person may choose to multiply A 5 times. We'll still get the same answer, and then find the determinant. We'll still get the same answer, but we'll take it down. Let's first find the determinant of negative 1, negative 1, negative 1, 3, negative 1, negative 2, 4, 2, 1. This one you can do it at your own time. I did this and found this determinant to be negative 2. So this is a determinant of A. This is that A. So what about that A raised to 5? This is the same as negative 2 raised to 5, which is negative 2. So at your own time, try and do it slowly and slowly. Like this, once you know this, it becomes very easy. We are given the determinant of this matrix and we are asked to find the determinant of this matrix. That means you must factorize this, work with this until you can express it in terms of this. Work with this matrix until you can express it in terms of this. Let's begin. We have 2A, B, C, 6D, 3E, 3F, 2G, H, I. I'm seeing something here. This is 6D. I can factor out. I can factor out this column. Now let me factor out this, not this row. Let me factor out the column 1. Let me factor out column 1. Factor out. Factor 2 out of column 1. So when you do that, I'm factoring 2 out. Column 1 becomes A. 3D, G. And this is B, C, 3E, 3F. This is HI. The next thing I want to do is to factor out row 3. I want to factor out row 3. So let me just get some space here. So when I do that, 3 is common there. But row 1 remains the way it is. What I'm factoring is this row 2, E, F, and G, H, I remain, column 3 remains. So I've already expressed, I know what this is. I know this determinant is 7. I know that the determinant of A, B, C, D, E, F, G, H, I is 7. So then I have 6 and 7, which is 42. And that is the required determinant of this matrix. Let's move to the last question. Now, so let's look at this other question. There are so many ways of doing this question, but I want us to use the knowledge of determinant, because I know that if the determinant is 0, then it means that the polynomial should be linearly dependent. So let me just write the coefficients of this polynomial. The first polynomial, 1, -3. No, it's 1, then -1, 2, 3. 1, -1, 2, 3. This one is 3, 2, 3, 1. This is -1, -1. And this is 1, 2. No, not 2. There's no x square. There's no x square, so it's a 0. And we have, for x, we have a 2, then a 2. This one I have 7. For x square, I have r. And for x, I have a 0. And then I have 5. Find the determinant equal to 0. So I think of the easiest way of finding the determinant. I can see I already have a 0 in this column, so I can create other zeros. So I want to create a 0 in row this position and this position. This is in row 3, so I want to get another row, the new row 3, by taking the current row 3 minus 2 row 1. Then row 4, I want to get it by taking the current row 4 minus 2 row 1. So when I do that, row 1 remains where it is. But this one also remains where it is, because it already has a 0 where I want it. Now multiply this by 2 and subtract from row 3. This by 2 from there, I have a 0 here. This by 2 from there, I have -7. This one by 2 from there, I have a 0. This by 2 is 14. From that, I have -14. -14. Let me just write it properly. Now, multiply by 2 and subtract from this. This by 2 from that, I have a 1. This by 2 from that, I have -7. Yes. Positive is 6. This by 2 from that, I have a 0. This by 2 is 14. From this, I have a -1. And this I equate to 0. Just some correction here. It's a -1 here, so this is supposed to be -1. This is also -1. Now, so now having this, I now want to get determinants along this column, plus, minus, plus. Let me find the determinant along that column and equate it to 0. So how do I get it out? Let me just the value there is 1. Remember, it's plus, minus, plus. So 1 into, delete this row and this column that has a 1. You have a negative 1, you have 1, you have 0, negative 7, you have a 1, negative 7, you have L, you have negative 14, and you have negative 9 equal to 0. We've succeeded in reducing a 4x4 matrix to a 3x3 matrix. Let's now reduce this 3x3 matrix to a 2x2 matrix, and then finally get our determinants. Now, so what am I looking at this time? I want to get a 0 in this position because I want to have as many zeros as possible in this column so that I have my work easy. There's the 1 outside, but it's 1 multiplied by something, just that something. So let me have negative 1, 1. How do I create a 0 here? By just adding row 2 to row 3. So current row 3 should be the new row, new row 3 should be current row 3 plus row 1. So row 2 remains. Now let's just add and we get a 0. Add and we have negative 6. Add and we have negative 9 plus A. Now let's now get the determinant along this column. Delete the row and the column of negative 1, and you have, let's put that here. When you delete those ones, you have negative 7, negative 14, negative 6, negative 9 plus 8 is equals to 0. Now there's a negative 1 here. So it's negative 1 into, multiply this, you have 63 positive, and that is negative 7A. Just multiply, I'm getting the determinant. And this would be 84, 86, or 86, it's 84, minus 84. Is equals to 0. So let's now create some space and do the final bits. Do the final bits of this question. So what I have is negative 1 into, inside the brackets, I have negative 7A, negative 21. This is equals to 0. So when I divide by negative 1 both sides, or even inside, if I do it inside, I will have 7A plus 21 is 0. That means that A will be negative 3. A will be negative 3. So that is what the question wanted. So A will be negative 3. And if A is negative 3, then these polynomials become linearly dependent. Remember that if we were to look for a condition that it will be linearly independent, then we will find the determinant should not be equal to 0. So that means H will not be equal to negative 3. That's how you are supposed to have tackled these questions. That's how you answer those questions. They are good questions, and I hope they have, by going through these questions, you've had enough exercise. But you can still do more by exercising more, find more questions from other books and try and attempt. Thank you for watching.